Okay, so we have a few different things we're going to work on this worksheet. The first problem that we're looking at, we've got a few different molecules, and our job is to determine which intermolecular forces are present, and we can select more than one force, and our choices are dispersion, dipole, and hydrogen bonding. So I'm going to try to keep this as simple as possible. Everything has dispersion forces. Like, don't even take a minute to think about dispersion. If it's asking, does this have dispersion? Yes or no? The answer 100% of the time is yes. They all have dispersion forces. The second easiest one for us to classify is going to be presence of the hydrogen bond. In order for a molecule to be experiencing hydrogen bonding, the molecule must have two criteria. So it must meet two criteria. First of all, it needs to have either an oxygen, a nitrogen, or a fluorine. And in addition to that, it needs to have a hydrogen on an oxygen, a hydrogen on a nitrogen, or a hydrogen on a fluorine. A lot of times we need to actually look at a Lewis structure in order to determine if a molecule can hydrogen bond because of the rules of the types of hydrogens that we need to have. But that's not going to be the case all of the time. So for example, with NO2-, there are no hydrogen atoms in this molecule at all, which means there's no way that it's meeting this rule number 2. Like, there's no way it's hydrogen bonding. And the same with NCl3, because it doesn't even have any hydrogens, it can't hydrogen bond. H2O, because it has oxygen and because it has hydrogen, it might have hydrogen bonding. It might not. We need to look at the Lewis structure for H2O, and I can just draw it right here. We need to make sure that the hydrogen atoms are bonded to an oxygen, and they are in this case, so there is hydrogen bonding. SF4, this molecule has fluorines, but it doesn't have any hydrogen, so there's no hydrogen bonding going on here. IF3, also no hydrogens. I3- doesn't have any of the right atoms, so no hydrogen bonding there. And the same with the last two. So if there's no hydrogen, you can't hydrogen bond. So only one of these molecules can hydrogen bond. Now, the next easiest thing I'm going to tell you, if a molecule can hydrogen bond, it's definitely also experiencing dipole forces. So again, like trying to approach this as simply as possible, everything always has dispersion forces. You can pretty easily tell if something has hydrogen bonding or not. And if it does have hydrogen bonding, it always has dipole forces every single time. Now, an absence of hydrogen bonding, so if you don't have hydrogen bonding, that does not tell us anything about the dipole forces. This could maybe be a yes, maybe it's a no. It just sort of depends. The easiest way to classify or determine whether or not it has dipole forces is determine whether or not the molecule is polar. So having dipole forces, that's just another way of saying that the molecule is polar. Now, a few videos back, we did go through, actually on the last worksheet, we went through and classified all of these molecules as polar or nonpolar, and that's what I've noted over here in the corner or on the sides, P for polar and NP for nonpolar. So if a molecule is polar, then it has dipole forces. And all of these molecules that we previously classified as polar, that means that they have dipole forces. And if you're like confused about what do we look at when we're trying to decide if a molecule is polar, just go back and go through this part again, watch that part again. That'll help you. So now what we're going to do for the next two questions is rank molecules in terms of their boiling points. And we're going to use number 1 for the highest and number 4 for the lowest. Now this has to do with intermolecular forces. If you have high boiling point, that means that you have strong intermolecular force. And of these intermolecular forces that we have up here, the hydrogen bond is the strongest. And dispersion forces are the weakest, and the dipole forces are in the middle. So when we're trying to decide ranking molecules in terms of boiling points, the first thing that we want to look at, let's start with the highest, we want to look for molecules that are capable of hydrogen bonding. And let's remember our rules. I'm actually going to drag these down to the bottom so we have them to reference. We'll just bring these rules down here. we want to look for molecules that have hydrogen bonding. Again, we're trying to find the one molecule that has the highest boiling point of all 4 of these. So looking at these molecules, we need to find molecules that have an oxygen or a nitrogen or a fluorine. We've got oxygen, we've got nitrogen, we've got oxygen, we've got fluorine, so we're good there. And then we also need to find molecules that have a hydrogen that's attached to an oxygen or attached to a nitrogen or attached to a fluorine. If we look at this molecule, all of the hydrogens are attached to carbons. I'm just going to temporarily cross it off. That molecule can't hydrogen bond because it doesn't have the right rules in terms of its structure. Second molecule, there isn't even any hydrogen bonding or hydrogen atoms, so we'll cross that one off as well. This molecule, hydrogens, we're looking for hydrogens that are on an oxygen, a nitrogen, or a fluorine. Look at that, boom, right there. We've got a nitrogen atom that has a hydrogen on it, which means that this molecule can have hydrogen bonds. I'm just going to make a note of that. Our last one, F2, doesn't have any hydrogen, so no hydrogen bonding there. Thank goodness only one molecule can hydrogen bond. That molecule has the strongest intermolecular forces. That means it's going to have the highest boiling point. So from there, where do we go? What would we do next? For me, personally, I think I want to go now to the molecule that has the lowest boiling point. So that's going to be the molecule that has the weakest intermolecular force. And for that, I'm going to choose the F2 molecule. I'm choosing this one partly because this molecule is perfectly symmetrical, and that typically corresponds to the molecule having the weakest boiling point. Also, this is the smallest molecule, just 2 little fluorine atoms, no other types of atoms. It's a very little molecule, which also corresponds to low boiling point, so little smallest molecule. Of the 2 molecules that are remaining, both of these molecules are polar, so they both have similar intermolecular forces. How am I going to choose between the 2 of them? The larger of the 2, the one that is heavier, that has the higher molecular weight, that one always has a higher boiling point. And the one that is lighter is going to have a lower boiling point. You got to kind of think about what's going on. Boiling means that we're taking this liquid and we're turning it into a gas. So the smaller and lighter and heavier a molecule is, the easier it will be for us to lift it up into the gas phase. If it's easy to lift it up into the gas phase, that means it's going to be happening at a relatively low temperature, which corresponds to a low boiling point. If it's hard to get these molecules up into the gas phase, that means it's going to require high temperatures, high boiling point. So we've got a couple more, another set of molecules down here that we can look at. Let's take a look at these ones. First thing we should always be looking for is hydrogen bonding. Not possible, not possible, not possible. This one tricks a lot of students because we have an oxygen and a hydrogen, but the hydrogens are not on the oxygen. So none of these molecules can do hydrogen bonding, which makes this kind of tricky. So now what that means, I want to go to let's look for the lowest boiling point molecules, the ones that are weakest, easy, small, little tiny molecules. We have another nice symmetrical molecule, just like F2. That one is the lowest. Now you might be thinking, whoa, what about this guy? That guy's really small. It's just one single atom. This is kind of a trick. This is cobalt, which is a metal. Think about cobalt. Think about any metal like gold or titanium or things like that. And you know those metals, even if you don't know cobalt, the metals that you do know, like iron, you know those substances are solids at room temperature. We don't typically even see them as gases. Like, it takes a ton of energy to boil cobalt. Imagine how hot that would have to be, hundreds and hundreds and hundreds of degrees. So this one's kind of a trick. Be on the lookout for tricks like that. Metal atom, those suckers are going to have super high boiling points, even though they don't have hydrogen bonds. And then we've got this little guy. Now we've got a couple other molecules as well. This molecule has just carbons and hydrogens. Those molecules, just carbons and hydrogens, typically have really low boiling points. When we get oxygen atoms in the molecule, or nitrogens or fluorines, even if they're not hydrogen bonding, that helps raise the molecule's boiling point. So a molecule like this is going to have a slightly higher boiling point, even though it's pretty small.